the random variable, one single random variable, and we defined the PDF and the CDF and the different functions that describe basically a random variable. We talked about when we condition on an event. We talked about also different random variables, binomial, Poisson, Gaussian, and so on. In chapter 3, we talked about the operations on single random variable, expectation mainly, and the expectation gave us basically a very powerful tool called moments. So the moments included the average or the expected value or the mean, the second moment, which is the mean square value, from which both we can calculate the variance and so on. And then we talked about the central moments, which one of them is the most famous one is the variance. And then we talked about the moment generating function or the characteristic function, how to generate the moments using a very easy way from the characteristic function. By simply differentiating the characteristic function n times, you get, and setting omega to 0, you get the nth moment. So basically this was almost chapter 3, and we talked also about some inequalities. In chapter 4, we defined the multiple random variables. As I mentioned at the beginning of the class, we talked about the joint and the marginal CDFs, the conditional CDFs and PDFs, and so on. Today, inshallah, we'll talk about operations on multiple random variables. So we'll start with the very similar to what we have done in chapter 3. However, it will be for multiple random variables. So the outlines for chapter 5 will look like, first of all, it's some introduction, and then we'll talk about expected value of a function of random values. Very similar to what we have done in expected value of a function of random variable, single random variable. However, now we talk about multiple random variables. We'll define the joint characteristic function. We'll define a very important concept called jointly Gaussian random variables. Very powerful, very important concept, and very used, especially when we talk about Gaussian random processes later on in the course, inshallah. And then we'll define the transformation of multiple random variables, how to find out the joint PDF of a transformation of multiple random variables. And then again, we'll come to jointly Gaussian random variables. However, when we have linear transformation for them. So if you have a jointly Gaussian random variables and you apply linear transformation through a matrix, then what will be the resulting random variable and the distribution and so on. And then we'll briefly finish the chapter with some sampling and limit theorems, very briefly. Okay, so this is basically our way ahead in this course. So just to cap up, to put things together for single random variable. For one random variable, we defined the expected value, which was basically the x bar or the expected value or the average or the mean. For the continuous case, simply we put whatever here, as we mentioned, next to the PDF, or next to, if it is a discrete, next to the basically probability of xi. Now, if we have nth moment, we define it as expected value of x to the power n. Simply x to the power n comes next to the PDF in the integral, and if you have it as a discrete, then basically the same x to the power n will appear next to the probability of xi. And the central limit theorem, mu n, which is expected value of x minus x bar all to the power n, we have it for continuous and discrete. And we have done so many examples for these subjects in chapter 3. Now, regarding the operations on single random variable, we defined the characteristic function and the moment generating function, if you remember. The characteristic function was the Fourier transform. So whatever inside the expectation as a rule, we just bring it here. And this basically defines the Fourier transform of the PDF. While the moment generating function defines basically, the inverse Fourier transform will look like, it will give you basically the PDF back. While the moment generating function is the Laplace transform of the PDF. Very similar to the Fourier transform, except there is no J here. So basically we don't take the complex exponential, we take the exponential only. And the way we use, if you recall, the characteristic function or moment generating function to generate moments for moment generation is the nth moment will be the nth derivative of the characteristic function will omega set to 0 and multiplied by minus j to the power n. And when we have a function of a single random variable, we have defined or put it in two different forms. The form when the transformation is monotonic. Monotonic means either it increases or decreases all the way. Or when it is non-monotonic. Non-monotonic is the most general case. So this applies for monotonic or non-monotonic. When it is monotonic, then the PDF of y evaluated at y is the same as the PDF of x evaluated at the inverse of y, which is x, which is t inverse of y, multiplied by the derivative or the absolute value of the derivative of the t inverse of y with respect to y. And if it is non-monotonic, then basically we do the same, except that we have n zeros, number of zeros of y equal t of x. Okay, so if you have 2 zeros, 3 zeros, you have 2 or 3 terms in the summation, and so on. So now, knowing all this, we would like to expand this for multiple random variables. So the first thing we start to do is to define the expected value of a function of several random variables, not a single random variable. So here we define, for example, g of x, y. G of x, y is a function of x and y together. Okay? It's a function of x and y together. So we define g bar to be expected value of g of x, y. And the way it works is very similar to what we have done in the single random variable. Simply, whatever inside the expectation comes next, however, next to what? The joint PDF. Because this is a function of two random variables. So you cannot take it with respect to a single PDF or marginal PDF only. So whatever inside comes in the integral, on the double integral, next to the joint PDF. And for discrete, guess what, Shabab? It will be for xn, for yn, it will be g of xm, sorry, ym, probability of xn, ym. This is for discrete. X and y. If x and y are jointly discrete. Okay? So this is basically the way we calculate it. Very similar to what we have done in chapter 3, except that we are dealing now here with the joint PDF of x and y, because this function, g of xy, is a function of both. Now, you can see from this equation that the single random variable was a special case only. So let's assume that we have a function only of x, a function of only of x, a random variable x. Then expected value of g of x, we apply the rule. However, assume that we have the joint PDF. We don't have assume that you have the joint PDF. We don't have the marginal of x. Then this basically comes next to here. Now, if we integrate, we can see that we can divide the integral into two parts, functions of x and function of y only. So we can here, you can see that you can differentiate first with, integrate first with respect to y. If you integrate with respect to y, what do you get, Shabab? What does this give me?
1.
لا مو 1. If I integrate with respect to y, what is this? شباب.
It will be fx of x.
It will be fx of x, the marginal of x. Remember دائما المارجنال كيف نطلعها when we integrate or sum over the other random variable. Okay, so this is fx of x. So basically this becomes the integral of g of x multiplied by fx of x. And this is what we have done in chapter same as in chapter كم؟ 3. عندكم اختبار بعد يومين، اليوم عليه عندكم اختبار بعد أسبوع على كل المنهج. Right? So basically this is what we have done already in chapter 3. The expected value of g of x is simply whatever inside here comes next to fx, because this is a function of fx, a function of x only. So we can see that all the operations on single random variable is a special case of two random variables operations. So you will see that chapter 3 is a special case of chapter 4. Very similar as we have seen that chapter 2 was a special case of chapter 3, chapter 4, sorry. كل الأشياء اللي تكلمنا عنها في chapter 2 we generalize it for two random variables or more. واضحة يا شباب؟ So if I want to generalize for n random variables, expected value of g of n random variables, I simply have n-fold integral, and we have the same as this function g of these n random variables multiplied by the joint PDF of the n random variables. أي سؤال يا شباب؟ طيب, let's see when we have a sum of functions. So this is like a special case. Expected value of a sum of weighted functions of random variables is equal, so the expected value of a sum of weighted functions is equal to the weighted sum of the expected values. خلينا نشوف إيش يعني هذه. So let's see expected value of summation of alpha I xi. So here what do we have? We have sum, this is called what? Expected value of a sum of weighted random variables. So this is sum of weighted random variables x1 x2 xn. كل random variable منهم له weight alpha I. Okay? Now, this expected value, we know that expected value operation is a linear operation, right? And because it's linear operation, you can get the expected value inside. أو بمعنى آخر ممكن أطلع الsummation outside. The summation, I can take it outside because it's a linear operation. And we get basically, this is equal to the summation of alpha I multiplied by the expected value of xi. And here is the proof of this. I can define this function, the weighted sum of xi, as g of x1, x2 up to xn. This is the function, right? So the expected value of this function is nothing but expected value of the summation of alpha I xi, right? And I know that this is equal to whatever inside here, I just put it, where is it? Whatever inside here, I just put it next to the PDF, except that I just took the summation outside. I can leave it here inside, but given that all these PDFs sum to or converge to a specific number, 1, then I can take the summation outside. فالمفروض إنه بدينا بهذه، بس إحنا we shortcut 2 steps here. تمام؟ So for every I here, what do I have? I have n-fold integral of alpha I xi blah blah blah. Okay, so if I integrate alpha I xi fx, this is equal to summation I equal 1 to n, as if I'm integrating a single integral. Okay, for a specific I, sorry, for a given I, all these integrals will become only one integral, because the rest will give you the marginal fxi. So I will have integral of alpha I xi fxi dxi, which is the expected value of alpha I xi, which is equal, because alpha I is constant, I can take it outside. So this is alpha I xi. So simply this gives me the result. Expected value of a weighted sum of random variables equals the sum of the weighted expected values. واضح يا شباب؟ أي سؤال؟ Basically, this comes straightforward from the concept. It's a direct result. Those of you who would like just to the simplicity, direct result from the linearity of expected value. This is a direct result of the linearity of the expected value. Simply because it's linear, I can take the summation outside. باختصار يعني. Now let's define the joint moments. Joint moments طبعا هنتكلم الآن بصفة عامة، لكن later we'll talk about very specific joint moments. So later we'll talk about very special joint moments that makes sense to us, that we can use to understand the relationship between two random variables. لكن الآن let's only define what a joint moment is. A joint moment of n plus k order. So this is a k plus n order. This is the order of the moment. mnk is equal to the expected value of x to the power n, okay, and y multiplied by y to the power k. So the first letter here, n, is the order to which you raise x to the power n, while the second letter is the order to which you raise y to the power k. Okay, this is called the joint moment, the n plus k joint moment. And it's defined as simply whatever inside here, we take it next, as we know, to the joint PDF. So this is the double integral of x to the power n, y to the power k, multiplied by the joint PDF. Or for discrete, it will be summation of all xn, summation of all yn. Now let's use other than n here. Xi, yj, xi to the power n, yj to the power k, then the joint probability of xi, yj, if discrete, x and y. Okay? So from here, we can see that the k plus nth joint order, joint moment is mnk, which is expected value of x to the power n, y to the power k. Now you can see that you can have all the different combinations of n and k. For example, if we set k to 0, so we have m, the nth moment. However, the n is the order of x. So we have what? Expected value of x to the power n, y to the power 0, right? Y to the power 0 gives you 1, which gives you expected value of x to the power n. While if we set n to 0 and k leave it as it is, then this will be expected value of x to the power 0, y to the power k. So the first one is the nth moment of x, while the second one is the kth moment of y. And you can see that these are not joint moments. If you set any one of them to 0, it's a moment of only a random variable, x or y. Okay? Now, if I'm interested in second order moments, second order means what? Means m plus k equals كم يا شباب؟ شباب في أحد معي؟
Yes.
طيب, send me over the private chat. Don't answer. Send me over the private chat. When I say second order, what does m plus k equal to? Over the private chat, شباب. Over the private chat only. For second order, what does m plus k means? شباب بسرعة لو سمحتوا. اللي ما أرسل. طيب. Most of you have got it right. So second order means m plus k equals 2. It's second order, okay? So the order here is n plus k. Then if I want m plus k equal 2, what do I have options? Either m equal 2 and k equals 0, or m equals 0 and k equal 2, or n equal 1 and k equal 1. Okay? So the first one here, m20 is what? What is m20? شباب, expected value of what?
K2 and N0.
Yeah, what is it? Expected value of what?
Y square.
لا لا, n2 y0.
X square then.
X squared, exactly. Which is the second moment of x. What about m02? So basically n0 k2. Expected value of
y square.
y squared, second moment of y. What about expected? What about m11? n1 k1.
y multiply x.
X multiplied by y, exactly. Now this is a very special one that we'll talk about it in the next slide. We call it correlation between X and Y. We'll come to it in a minute. Okay? Now the first order moment. First order means what? N plus k equals 1 is equals كم؟ هذه n and just اكتب m.
1.
N plus k equals 1, right? So I don't have many options here. Either n equals 0 and k equal 1, which gives you the expected value of y, or n equal 1 and k equals 0, which gives you the expected value of x. You don't have many options here. Okay? So now, if you recall, if I have a PDF, then x bar, if this was a PDF, x bar was like, as you mentioned, the mean, right? Or we can think about it as the center of mass, center of gravity for this PDF. Now, if I have a double or two random variables, x, y, and I have the PDF, then x bar, y bar will look like the center of gravity, where most of the PDF is focused. The center of mass, the center of gravity of the joint PDF. Okay? Think about it that way. يعني if xy like a body, then x bar, the point x bar, y bar will look like the center of mass. طبعا you can generalize for three random variables, m3, 2, 5. So this is about what? 3 plus 2 plus 5, which is كم? 10, right? This is the 10th moment. 10th joint moment of x, y, of x1, x2, and x3. And this is simply e to the power x1 to the power 3, x2 to the power 2, and x3 to the power 5. واضح يا شباب؟ Any question? Now let's talk about a very specific joint moment.
What is
اللي هي
it? 1 and 2 and 3, Doctor?
نعم again.
x1 and x2, x3 is what in the coordinate?
Three random values. 3 random values. Any 3 random variables. إذا أبغى ال 10th moment with 3, 2, and 5 according to this, then this is expected value to the x of x to the x1 to the power 3, x2 to the power 2, x3 to the power 5. So بدل ما كان عندي x و y أنا هنا I defined 3 different random variables, x1, x2, x3. تمام?
Yes.
Now we define a very specific, a very special joint moment اللي هي correlation, which explains the dependence between two random variables. اللي هي M11. This is expected value of x multiplied by y, which is simply whatever inside, we take it next to the joint PDF. Okay? And if you have discrete xi, yj, this will be expected, this will be, sorry, xi multiplied by yj, sorry, the PDF, the probability of xi, yj, discrete, x and y, تمام? And this is denoted as Rxy. We'll use this all over the rest of the course. Rxy is the correlation of x and y. Is the correlation of x and y. Okay? Now, if Rxy, which is expected value of x multiplied by y, equals the product of the expected values of x alone multiplied by expected value of y alone, then x and y are uncorrelated. Then x and y are said to be uncorrelated. Uncorrelated يعني ما لهم علاقة ببعض. لكن it is much weaker than the concept of independence. We'll come to the difference between them in a minute. Now we will prove next time that independent random variables are uncorrelated random variables. However, the opposite is not true, not necessarily true. So independent means what? The joint PDF equals the product of the marginal PDFs, fx, fy. Now, if this is the case, then the correlation will be the product of expected value of x multiplied by expected value of y. Okay? And the proof for that is the following. Expected value of xy is what? Whatever inside comes next to the joint PDF. Right? Now, if these are the x and y are independent, means what? If xy independent means that the joint PDF can be written as the product of the marginals, right? So this will allow me to separate the two integrals, to decouple the double integral into one integral with respect to x multiplied by another integral with respect to y. Right? And this, the first integral is nothing but the expected value of x, while the second integral is nothing but the expected value of y. So if independent random variables, they are uncorrelated. Random variables. And here comes independence gives you uncorrelated. The opposite is not true, not necessarily true. It might be, it's not necessarily. شباب ابدأ افتحوا الكاميرات. So next time inshallah we'll continue from here. كاميرات شباب. We have 2 minutes only.